topic of this video is about a method on identifying equivalent states, and this goes towards minimizing a given automaton for a recognizable language. So this is really all about equivalent states, and I'm going to have for you a sequence of results that eventually is going to give us really the minimal number of states that one needs to recognize a given language. And remember that we were saying, for an automaton A, this was given by Q sigma delta Q0 and F, and we were saying that P and Q, two states of this automaton, we were telling that they are K distinguishable if there is a word U in sigma star of length at most K in such a way that when you do a computation in P from P and a computation, so this might take you to some state R, and you do a computation from Q on this word. So these two computations, if the computations this and that, they are so of the computations, these ones, one is accepting while the other is rejecting. And we were telling that P and Q are equivalent if they are K indistinguishable for all Ks. So the point I want to make here is that you're going to start looking, at K equals 0, and you will say, if I don't even look ahead, can I make some distinctions between the states? And you really have a very blunt instrument here. You don't even look ahead, and so you will not distinguish too many categories. Maybe you will distinguish something like 2 categories, and there are a lot of states in here, and you know that there is a difference between these ones, but you don't really know in between these ones because you have such a blunt instrument. But then you have a better instrument. You say, I'm going to look ahead one step, and all of a sudden you realize, these differences, they remain differences also here, but you all of a sudden realize that, hey, I can actually make a difference also in this state, in this category, and maybe I can make even more of a difference in this one. And then you say, let me take even a sharper instrument, K equal 2, and all of a sudden you can distinguish even more. You just keep going like this. And we will discuss how long this goes. But this is an intuition I would like you to keep in mind as I'm giving the results I need to give, that really when I talk about 0 distinguishable and 1 distinguishable, you think about the power of your instrument. If you say 0 distinguishable, you really don't have much power. But when you say 1 distinguishable, you're allowed to look ahead at most 1 step, and then you might actually distinguish more than what you were distinguishing before. So this is a good insight to keep in mind as we go through the next results. And so here is the first result I want to give. This is lemma, in your lecture notes, this is called lemma 3.49. And yeah, it's saying this, that P and Q are K indistinguishable if and only if we have these two conditions. PQ are both final or both non-final states, right? Because they are, I mean, indistinguishable. So if they were one final, one non-final, then you could distinguish. So they are in the same category from the point of view of the final states. Either they are both final or they are both non-final. And you have a second condition, which says if K happen to be greater than 0, then delta of P and A, so this state and this state, are K minus 1 indistinguishable for all A from sigma. So what this means is that if K is bigger than 0, then you really have no way to distinguish between P and Q. In the case when if you take a step ahead from P and a step ahead in A, those states that you have, they are K minus 1 indistinguishable. By looking still ahead from those states, K minus 1, still you cannot make any difference between them. And when formulated like this, when interpreted like this result is almost obvious. But I'm going to give it a proof anyway, just to fix these ideas. So let's assume that we have these two states P and Q, and they are K indistinguishable. And to prove point 1, if, for example, P is final and Q is non-final, then really you can distinguish them. So they are, in fact, then they are really K distinguishable, because really delta of P and epsilon is accepting. So that's an accepting computation, or in fact this is a final state, and doing a computation from Q with epsilon is rejecting, meaning that this gives you a non-final state. So and K distinguishable, it means that you could do this with words up to length K. So you can certainly do it with epsilon. So really the first condition is satisfied. You cannot have them one final, one non-final. They have to be both final or both non-final. Now, if K is bigger than 0, so what you have in there, let's say assume that this state and this state are in fact K minus 1 distinguishable for some A. What this means is that from R, there is a word V, of length at most K minus 1, that takes you to some state alpha, and S may be with the same word. Takes you to some state beta, and out of these, one is final, the other one is not. So that's what it means that they are K minus 1 distinguishable. But then remember that R was obtained by going from P with letter A, and S was obtained by going from Q with letter A. So what this means is that on this computation, the word AV takes you from P and from Q to two states. One is final and the other one is not. So this implies, remember, the length of AV is at most K. So that implies that P, Q are K distinguishable. And that's a contradiction, because in fact we had this hypothesis that they are in fact K indistinguishable. So that's a contradiction, and so our assumption was wrong, and that proves the second point. So I would like now to introduce formally the idea of this equivalence relation that I mentioned in the beginning of this lecture. So I will have this definition, and I will just define some equivalence relations. And I will define really, in principle, an infinite sequence of such equivalence relations: equivalent 0, equivalent 1, equivalent 2, and so on. And these are equivalence relations over Q, over the set of states Q. And they are defined in the following way. So I will say P is equivalent to Q in the zero equivalence, if and only if both EQ are in F, or both EQ are not final. And I will say now in the K plus 1 equivalence, I will say that P and Q, they are equivalent in this equivalence relation, if and only if they are equivalent in this one, and delta of PA is equivalent in equivalence relation K with delta of QA for all A in sigma. And obviously you can take it just as a formal definition, or you can build on the intuition I gave. And in fact, I'm going to still dwell on that intuition in just a moment. But maybe for now, it's just enough to realize that these are these are well-defined concepts. I define it for class 0 with a direct definition, and then I have an inductive definition. The equivalence relation K plus 1 is defined in terms of the kth equivalence relation. So that's certainly, these are well-defined concepts. And here is where I'm going back to my intuition. So this is in your lecture notes, lemma 3.51. And what this lemma says is, look, in these equivalence relations you have defined here, so P is equivalent to K in this case relationship, if and only if P and Q are K indistinguishable. And so that was the intuition that I was alluding to in the beginning of this lecture. And we can prove this. And the proof is going to go by induction on K. And that's no wonder, right? Because the definitions were done inductively. So certainly we have the structure to do this induction on K. And so for K equals 0, the matters are pretty easy. For K equals 0, we had P is in the 0 equivalence with K, if and only if EQ are in F or EQ are not in F. And so this is if and only if really these computations on the empty word, so on the only word of length up to 0 that you can have. So if these ones are in F at the same time, or they are not in F at the same time, and so that really means that P and Q are 0 distinguishable. 0 indistinguishable, I'm sorry. right? So now if we take k larger than 0, and we assume the claim holds for k, and we are going to prove it for k plus 1. So if we have P in this equivalence k plus 1 to Q, so what this implies is that by definition, P and Q, they are in this equivalence, K, and delta of PA and delta of QA, they are in this equivalence K. This happens for all A in sigma. This is just the definition. And what this means is, on one hand, because this holds, so we have PQ are K indistinguishable, and we have that delta PA and delta of QA are K indistinguishable for all A in sigma. And just by the previous result I proved, this implies right away that P and Q are K plus 1 indistinguishable. So for the other implication, if I say, well, let's take P and Q to be K plus 1 indistinguishable. So just by default, if you cannot distinguish them by looking ahead K plus 1 steps in computation, certainly you cannot do that by looking just K steps. So just this is a trivial implication. PQ are K indistinguishable. And also, by the previous result I proved, it also, you have this implication that delta of PA and delta of QA are K indistinguishable for all A in sigma. And that just gives us, by induction hypothesis, that really P is in this class K with KQ, and delta of PA is in this the same equivalence class with delta of QA, and that goes for all A in sigma. And that just by definition, it follows that P and Q are in this same equivalence class in a K plus 1 equivalence relation. So we got the other implication, so the result is proved. So one thing that we kind of went quickly over, but I want to just point it out to you, and I'm just going to write it as a lemma, but we have already discussed about this. It just says that, you know, if P and Q are in this equivalence class, then certainly they are in this equivalence class. And so this is just a reformulation of something I already mentioned in this lecture, because if they are in this equivalence class, it means by the previous result that they are K plus 1 indistinguishable. And if you cannot distinguish them by looking ahead K plus 1 steps, you certainly cannot do it by looking ahead just K steps, so they are certainly K indistinguishable. And again, by the previous result, it means that they are in this equivalence class K that we have defined. So this is certainly true, but consequently, what this means is that if you think about this equivalence relation, just because of this implication, that certainly this includes all these equivalence relations like this. and this certainly includes this one, and so on. So as you go to higher index, then you are going to have smaller and smaller relations. And finally, the last result I want to just prove is this. And it goes like this. If you have this equivalence relation K to be exactly the same as this relationship K plus 1 for some K, then all the other relationships are going to be exactly the same as K. And I want to explain what this means. The proof is basically already in this intuition I give you. What this means is that you have these indistinguishable states by looking ahead K steps, and then you say, let me look ahead one more step, and all of a sudden you cannot really distinguish more than what you had in here. And remember that these relationships, they are defined inductively. Each one of them is based on the predecessor. So by looking ahead one more step, you couldn't really distinguish anything anymore. So it's exactly the same equivalence classes as you had before. And so if you did one more step, then again it means that you start from this one. And it didn't make any difference starting from this equivalence relation to take one more step. You couldn't distinguish more. So by taking more and more steps, it means really that you always are in the same situation, and that is to take one step from this equivalence relation. So that's why these equivalence relations, they all collapse to the kth level for all n greater than or equal to q. I can certainly give a proof. You have it also in the lecture notes. This is in fact lemma 3.53 in your lecture notes. And the proof formally is like this. So if you have, so remember that we have assumed in our lemma that these two equivalence classes are the same. And so we have like this. So if P is in this relation with Q, meaning P and Q are K indistinguishable, then it means, because we have this equality, that P and Q, they are also Q plus 1 indistinguishable. That's what this equality means. And by having them K plus 1 indistinguishable, what this means by definition, so this is the assumption, if you like, the assumption of the lemma that this equality holds. And this is now by definition, this implies that delta of PA is in this equivalence relation with delta of QA for all A in sigma. And again, this by assumption, by our assumption that these classes are the same. So it means that delta of PA is in this K plus 1 relation with delta of QA, and that goes for all A in sigma. And now if I think about the relation K plus 2, this implies right away that P and Q are in relation K plus 2. And so what this means is really that this relation K plus 2 is all of a sudden the same as relation K. And now we can iterate the argument, and we see that you are always going back to this relation K. So what this means, again, the proof is otherwise concluded here. So what this means is that you start with these indistinguishable states that you can observe by essentially doing nothing, by just looking at them. Are they final or are they non-final? And essentially you are going to have exactly two categories, two equivalence classes in this equivalence relation. One is made by the final state and the other one by the non-final state. So by doing nothing, you have no way to distinguish between these ones and no way to distinguish between these ones, but you certainly distinguish between the two. And then I'm saying you will get to this equivalence class, and you can now distinguish more potentially. So maybe you distinguish a little bit more in this category. But in any case, if you have two states in the same equivalence class, they certainly were in the same class in here. So that's what this inclusion means. And then you say, let me just go even further. And at some point you get to this one. And the crucial observation here is that you cannot really continue this forever, because you cannot have more equivalence classes than the number of states in your set Q. You cannot, in the best case, you can distinguish between all of them, and that's going to bring you to n classes, exactly as many states as Q has, but you might also stop earlier. Either way, at some point when you go in this construction, you are going to collapse. You cannot really continue forever. And that's the sign that anything else after this, it's also going to stay the same. So what I'm saying now here is that you are going to look ahead and you are going to try to distinguish between these states until eventually you are going to get to this level where looking ahead doesn't help anymore. You cannot really distinguish anymore. And that's going to give you all the equivalent states in your automaton A, the one that you started with. And by eliminating those equivalent states, that's going to give you the minimal automaton for the language accepted by A. And I realize that this stays for now on a very abstract level, but let's take an example, and we will have some more examples in your demo sessions. So here is one example. And I take the example from your lecture notes and I go over it. So the automaton I take is going to be defined in this way. I just draw it visually here. So I have state 0. This is the initial state. And I go with A into state 1. And I go with B into state 2. And in state 1, I stay with letters A. And in state 2, I stay with letter A. And then I go with B from here to some state 3, which happens to be the final state. And from state 2, I go with letter B to state 3. And in state 3, I just stay, with letters A, B. And so if I think about, first of all, the equivalence relation 0. So what this was about was, by doing nothing, I mean, you cannot really look ahead in the computations of this automaton. What can you distinguish among? And you can basically distinguish two classes. One is you have the equivalence class made of states 0, 1, 2. These are all non-final states. And the other class you have is made of state 3. So what I mean by that is that these states 0, 1, 2, they are equivalent to each other in this relation. And 3 is just equivalent to itself. There is no partner for it. And then what we have is, when I go to this one, all of a sudden I see that I can distinguish between state 0 on one hand and states 1 and 2 on the other hand. And so this one will have now one equivalence class made of just 0, one equivalence class made of just 1, 2, and one equivalence class made of just 3. And the reason I have this is because if I start a computation from 0 with, I'm allowed to have one letter, right? And so I will take with letter, say, B, for example. From delta with, from 0 with B, I go to 2, which is non-final. But if I go from 1 with B, I get to 3, which is final. And so I distinguish between 0 and 1. And also I distinguish between 0 and 2 with the help of the same computation. From 2 to with B, I get to a final state. And it's not too difficult to check that, in fact, I cannot distinguish with letters of, with words of length 1. I cannot distinguish between these ones because taking letter A brings me back to the same set, and taking letter B brings me to the same state no matter where I start from. So it doesn't help. And when I think about this one, meaning I would like to distinguish now with with single letters between 1 and 2, then you realize that you cannot do that, and you just get exactly the same equivalence relations as before. And that's the sign that you have to stop, because you just got the same equivalence relation on level 1 and on level 2. So the conclusion you have is that state 1 and state 2, they are equivalent in the automaton A. So you can remove one of them. So let's say that we remove state 2. And what we will have is simply this automaton. So 0 remains unchanged, is the initial state. And now I'm going to go with letter A to this state. But remember, they are put together, or if you like, one of them is modified. But let me just think about it in terms of putting them together into a single state. So this is the state, if you like, let me just put this label so that you realize. So with letter A, I go to this state. And with letter B, I go to the same state that I just now put together. So it's AB. And in this state, or in fact, I can focus on just one of them. With letter A, I stay in here. And from this one, I go with B to 3, which stays exactly the same as before. And this is a final state, and I stay with AB in this one. So that's the automaton, which is equivalent with this. And as a matter of fact, this is the minimal automaton. So minimal automaton, recognizing the same language as the automaton that we started from.